Hi again. This time I'm going to tackle a different kind of a project. The Arduinos are new to me. I basically got into designing with them just about 2 or 3 weeks ago. And I started off with an Arduino Uno, which I had lying around for a long time. Hadn't done much with it. So I decided to build something with it initially, and it seemed to work. So I translated that design to an Arduino Nano, which is smaller. As you can see, as most of you know, the footprint is smaller and it's got some different features, but essentially they are pretty much the same. The sketches that you do for the Uno can be used for the Nano as well, with minor differences sometimes. Anyway, this project is about building an Arduino Nano altimeter. So I'm a pilot, and I find the use for altimeters, and I've experimented with that for in cars as well as to design a airspeed indicator for EVs. You might have seen that video before. So I thought I would build altimeter with that. It's can be pretty accurate actually, based on what I've seen so far, if you use the correct sensors. Anyway, so let me just describe this particular design over here. So we have the Arduino Nano, which is the main processor, and one thing to remember is that there are different versions of the Nano. The one that is built by the the company that is originally developed it, uses a different driver for their chipsets. So these are clones essentially made in China, and you can see that they use different drivers, and they call the CH340 drivers. And sometimes to make them work in the PC, you'll have to use an old bootloader. So those who are familiar with Arduino would know what I'm talking about. In any case, I will try and describe what I've done in the software portion of it a little bit later. Anyway, this is an Arduino Nano 3.0 with the CH340 drivers, and using the old bootloader to load onto a Windows laptop. Anyway, so here's the overall design. We have the Arduino Nano, and then we have the three other blocks that I need to make this work. One is the BME280 sensor. This is pressure sensor, humidity, and temperature. So it's got three different sensors on it, and I'll go through the pins a little bit later. The second unit is the display, which is the SSD 1306 0.96 inch monochromatic OLED display. Maximum resolution is 128 by 64. And the third component is a rotary encoder. So I'll talk about this, why we need it in the design itself. And this is a hookup is shown as here, and we have the main ports over here for the sensor, the SDA, which is a data line, the I2C design, clock, and ground and supply, and all the supplies here are 5 volts. For the OLED display, we have the ground, VCC, again this is plus 5 volts, and we have a clock and a data. And because these are I2C, these are addressable kind of a serial interface. They can be connected together, and they go to the A4 and A5 ports of the Arduino Nano, which are the I2C ports, also called SDA and SCL. And there's a 5 volt supply, the ground, which are common. The ground is in green. Sorry, it's not visible very well over here, but essentially the grounds are just a simple connection among all of them. I try to minimize loops as far as possible. And it can be noisy, especially the encoder. If you see some noise with the encoder, you might have to make sure your ground and supply connections are good, not coupling into any of the clocking lines and so on. So that's one only thing you need to worry about or pay attention to in this board layout. And finally, the encoder itself has data and a clock, and this you can use digital pins for that. And the ones I use are D3 and D2. And then there's the switch, which is actually a toggle switch for the push button on the knob itself. I'm not using that. And there's a plus and a ground. So plus is 5 volts, ground is 0 as before. So this is the entire design. You can see the hookups are simple. You just have to connect all the supplies together, the grounds together, and then you have the A4, A5 lines going to the data and clock lines. And over here, this data and clock do not use this data. This is not a smart device, I believe. It's just got some encoder with some timing waveforms which are created, I believe, by the Arduino Nano. Okay, so before continuing on into the actual implementation and so on, I would like to talk a little bit about pressure itself. Briefly, it's a complicated topic. It's beyond the scope of this video to get into the weeds about different types of pressures. There's we talk about absolute pressure, pressure altitude, density altitude, and all kinds of things like that. But anyway, in this instrument or device, we are measuring absolute pressure with the BME280, and we need to convert it to a pressure altitude. The pressure altitude is what we are interested in as far as the altimeter is concerned. Practically speaking, pressure altitude is the altitude you read on your altimeter when it is set to 29.92 inches of mercury or 1013.25 hectopascal or millibar. This is also known as a standard pressure at sea level. Since for any given day or time this atmosphere is not standard at sea level, it can be varying up and down tenths of an inch, maybe more, depending on the weather systems that are around. The difference from standard pressure, that which is 29.92 inches, must be accounted for, or all your altitudes will be off because of that variation at sea level itself. So that is what the altimeter setting does. It basically compensates for that change in pressure from the standard pressure. In the aircraft, basically, we have an altimeter. The altimeter itself has a Colesman window, which is like a dial, which allows you to dial in this altimeter setting, which then moves the needle appropriately to the right altitude. So where this, whenever this setting changes, you have to make sure you also update that altimeter setting, and this happens periodically, and as a function of time, as well as when you fly somewhere else or when you drive somewhere else, the actual pressure would have changed because of environmental reasons. So one has to basically keep adjusting that, and how frequently that changes or how fast it changes, the more frequently you have to do that adjustment. Anyway, the last thing to mention here is that the altimeter setting does not account for temperature changes. That's a separate issue, and the altitude that is reported for temperature changes is called density altitude, and that's an important aspect for planes, because anything that cools or heats also changes the effective pressure in the atmosphere. Cold air is denser, so it's got higher pressure, and hot air is lighter, it's got lower pressure, and the amount of molecules that are there affect the lift of a plane or the engine performance and so on. So that is kind of important as well, and that is reported in some cases in certain airports which are very high elevation, where the combination of a low pressure altitude, low pressure at which is a high pressure altitude, along with high temperature, can actually make things pretty difficult for planes to take off, and also causes planes to have a longer landing distance and so on. So that's just a side deviation about pressure, and so let's now get back to the main discussion about this altimeter. Okay, so now at my location, which is 350 feet above sea level, you can see as the pressure of the atmosphere changes up and down, the Arduino, this altimeter would read different values, and so you have to periodically adjust this rotary encoder to set sea level altimeter setting to make sure you're reading that same altitude, because altitude is not changing, it's just the pressure that is changing. So you can do that in a fixed location. But if you're flying along or you're traveling somewhere, you don't know what the altitude is, so you have to take the sea level altimeter setting, which is usually published in various websites, META reports and so on for pilots, and you can use that setting to basically get the true compensation you need to do for that location, for that particular air pressure that is at that location. So that's the background of the altimeter. The code then essentially reads all these two instruments and then displays these two devices and then displays the reading on this OLED display. You can see over here I'm measuring at my location, which is 350 feet. In addition to that, I have this altimeter setting 29095, which is what I can adjust using the rotary encoder. So if I turn this around, I can change it to 29.92 or 2992, which is a standard level, sea level standard temperature pressure reading, or I can go up and down whatever the conditions dictate for that location. And then there's a temperature output and there's a dew point output. So these are also important, and we like to know that for pilots, as this kind of gives you some idea about possible cloud levels. Humidity itself is not a useful term because it doesn't tell you anything about how close your dew point is to the temperature, and that varies over the temperature range. Depending on the absolute temperature, the dew point is more indicative of how far you're from saturation of the atmosphere. So I like to have the temperature and the dew point for evaluating cloud levels especially. So, and then the final thing is you need a USB mini connection, which is on the Arduino Nano itself. You can drive that 5 volt supply with that, and also this serves as a means to program the Arduino board with the software that you have. So next we'll get into the board itself and the software. So here's the prototyping development board for using the Arduino Uno, and you can see it's a jumble of wires. I'm not going to explain anything because I've removed some of the components in there. The only thing that is remaining here is actually the pressure sensor, which is down at the bottom here, and I have a few spares. So that's the BME280, which is very small. It's about a centimeter by a centimeter and a half in terms of dimensions, and as you can see the temperature sensor on the bottom left, a very tiny little device, and then there are the connections to the Uno itself. You can see that's there's no point going into this, it's just too messy, but this is what I developed, the initial prototype design for the software, and then I migrated this to the actual working version, which is over here now. You can see it's a little bit cleaner, smaller. So let me just quickly explain what is here. We need to improve the lighting here. Okay, so hopefully you can see this better. So on the bottom left is the sensor again, the BME280. Above that is the OLED display. It's monochromatic. There are 4 lines you can see on top, the same clock, data, power supply, and then on the right side is the encoder, and that again has this knob which is infinitely, you can turn this as much as you want. It just doesn't have stops on it, so you can depending on how you program it, you can get different step sizes and so on, and it's very useful for this kind of application. It's electronically controlled. I didn't have to write anything because I don't want it to have a fixed value, because that keeps changing. If you have a fixed value, it's pretty much useless as an altimeter, but it's good as a pressure sensor if you're just looking for absolute pressure. And this is a very accurate, the BME280 is a very accurate pressure sensor from what I can see. It's a MEMS device, I believe. The other side is, you can see the messy wiring, but everything is connected right now through standard wires, 30 gauge AWG wires, and have some hot glue to just hold them in place for now. This is just a prototype board again, and that's the Nano, tiny device, about 2 inches by half an inch or so. So let's next power it up, and I'll show you what it looks like. So what I did for the power is I built using a simple 18650 3.7 volt lithium ion cell. I under this is one of those boost converters, which unfortunately I taped it up. You can't see it, and maybe I have a different. I'll show you another picture of that later. But this is just a I think MT3806 boost converter, which you can buy for 50 cents, I believe, something like that. And I stepped it up to 5 volts, and then I'm applying it through this USB mini output to the Nano. So that's, I think the Nano, this whole board consumes about less than 30 milliamps if I recall. So this particular battery or cell can drive this for many hours easily. So let's use that to start this up. So you can see it comes up with a splash screen, and then it goes into the display. And so that's the display of the altitude. Right now it's defaults to 2992, which is the one I told you about, is the standard pressure for any for the standard setting. It does not reflect the true pressure at sea level today, right now. So, and it's the temperature below, it says 27.5 Celsius, dew point 10.6 Celsius. Okay, so it's fairly accurate. I checked the actual temperature within a few degrees, as fractions of a degree with real. There's some self-heating going on in this sensor, so you can expect some variation of plus minus plus half a degree, I believe, something like that. So I'm going to change the setting down to what it should be right now. It's 2985, I believe, right now at this location. So as you can see, the altitude is reading 352, which is close to my 350 is actual altitude at this location. So it's around. I don't particularly trust the last digit. It's not very useful, especially if you're a pilot. You probably care about the tenths and above. But you can actually sense down to a foot level accuracy or resolution very easily with this sensor. It's very accurate. For example, if I can let me take my camera off the stand. I can show you what happens if I move it to the floor. This is about 2 feet off the floor right now. It says 352. As you can see, it's 350. That's about 2 feet down. So this is very sensitive, and I did some moving average calculation here, so it doesn't jump around too much, but you can see it will still move around a little bit. But it's within, the jitter is very small in terms of the variation. It's now pretty stable at 350. So that's good. I'm bringing it back to the table. And it's back to 352. So I also tested it driving it around the neighborhood. There's a 50 feet elevation around this area, so when you go up to a different part of this area, you can actually see that responding pretty quickly to the altitude changes. So it's very sensitive. The main thing is, as you go higher, you probably don't look at that last digit. It's going to vary too quickly, especially if you're flying or driving around. So here's my software, version 1.1. This is for the Arduino Nano, as you can see on top. Just be forewarned that I'm not a good programmer. I have been doing this for the last 2 weeks. Picked up a lot of stuff on the internet. When I ran into issues, I still have issues with sometimes programming the thing. It won't program, even though it sees the COM. You can see over here, it's not connected right now. It's on COM 4. Initially, I had to change the bootloader. One of the things I had to do was here. You can see you can use the old bootloader, or for the genuine article you use this one. So it depends actually. Some of the Arduino Nanos work even with this one. Depends on the version, I guess, and the drivers, and it's a bit complicated for me. I'm not a software guy. So anyway, if you use the old bootloader, generally it seems to work. And then, so the sketch really begins on over here. There are a bunch of include statements for various hardware options. One of the things I also had tested was Bluetooth, which actually works, but I have disabled it for this one. I don't need a Bluetooth. I'm going to have just a display on that OLED display. So like this one, the software serial.h and Adafruit sensor, I think you need that for the Bluetooth. Sorry, SPI.h maybe. Anyway, I've confused which include files are for what, but the SSD 1306 is obvious for the OLED, and then there's the BME280 for the pressure sensor. The rotary encoder does not require any libraries, but you have to define the clock and data inputs, as you can see here. And I also defined here the screen widths and screen height, some OLED reset. This is the default I used, and this is also another default for the OLED. And then down here, this is for the Bluetooth 8C05 Bluetooth device. It's not connected right now, so you can ignore this. There are some variables I declared for the basically for the rotary encoder. You can see the A state, A last state. The array size is for the moving average depth, and there's an array for that. It's defined as a 6-bit array. The altimeter setting default is 29902. Also, there's some calibration error or the absolute error in the sensor reading, so I compensated for that by using a variable for that. And if you use this, you may have to tune that for every sensor that you have. And then this one is for Bluetooth, again declaring the software serial for BT serial. That's the port that you're going to use for writing to the Bluetooth. The BME Adafruit is declared here, and there's a void setup. You start declaring all your variables and the assignments for the pins. So you can have the RX pin and TX pin for the Bluetooth, which is not used, as I said. The pin mode for the clock and data for the rotary encoder. Then you have the serial begin, which is a baud rate or for the serial monitor, and then the Bluetooth serial also you can define that also the same rate 9600. Then you have the encoder set up for the you essentially assign this A last state to the digital read of the clock, and you attached some interrupts for that. So anytime you change the knob position, it actually will interrupt the program and update it. Without this, it's a bit tricky to get it to work while it's actually running the main loop. It may not interrupt it, and then you won't see any change on your altimeter setting. So you want to be able to update the altimeter setting anytime you want. So you need the interrupt here. Then the detection of the BME280 is shown here. Just an error. If you don't find it, it will actually print this out. Then next is the OLED display. So all the display dot functions are basically you're using it to display on the OLED thing that you want to show. And there are some initial assignments here, like the address and then the color, text. I believe it's monochrome, so I think it doesn't matter here, but there's the clear display and the text size, and then you can do some initial display, that is the splash screen, which I do over here, version 1.1, and then I wait, and then I clear it. And that ends that initial setup for the display. And for the encoder, you can see there's some, this is how it reads the movement of the knob. So you can see it assigns the current state to the last state, and if this is true and the state is equal to 1, then it will. So basically, I had to go through this code. I copied it from another program, and so it either decrements or increments the counter depending on what the state of this digital readout is for the data pin of the digital read of the encoder, and it either assigns it to increment by 0.01 inches or minus 0.01 inches. So this is the altimeter setting in inches, and then if it on the serial monitor print out that change over here, the altimeter setting to 2 digits accuracy, and also do that on the Bluetooth if you have the Bluetooth connected. Then it assigns the current state to the last state. Then the void loop starts. This is the main loop. Clear the display for the OLED. I have some assignments, some variables here. The altimeter setting in hectopascals, altimeter setting in inches times 33.8639, which is a constant. Some other floating point variables here: temperature, pressure, humidity, dew point, altimeter reading, altimeter sum. This is for the moving average. I'm summing some stuff, the integer for the counter. And then I start the moving average calculation. I read the altimeter reading from the BME280 in hectopascals, and then I multiply that by 3.281 to convert it to feet, times subtract the error, which is negative or positive depending on what you have in your variable for the altimeter error. And then I do this moving average loop where I'm shifting the value through the array. And then finally I assign the 0th array to the current altimeter reading. And then that keeps propagating through the chain as the loop runs through. And then at the end, after this, if I do it in this particular case, I do it 6 times, so successively, quickly. And then I essentially calculate the average over here. Sorry, I'm summing it over here, the values, and then I'm divided by the array size. In this case, it's 6. So the altitude is actually the sum over 6 readings and divide by the array size, which is 6 in this case. The pressure, same thing. You read the absolute pressure, hectopascals, and then the temperature is read here, the humidity is read here, the dew point is a calculation that you can do using the humidity and the temperature. So this is a fairly complex equation. You can use this to calculate the dew point, which is what is interesting to me. By the way, the BME280 has internal formulas to do the conversion from pressure reading to the altitude. So that is again a fairly empirical type formula which you can read on the internet. I won't get into that, but I've tried that as well, and it should work if you actually want to use the calculation using the pressure reading itself, which is over here. But it's tricky. You might make some mistakes. So it's better to use the built-in function here. And then if you want to look at it on the screen, you can then do the serial print, which is the temperature, altimeter setting, altitude, humidity, and so on. So this is something, if you want to look at it while you're debugging it, you can do that. With the Bluetooth, same thing. You have some which is commented out over here. You can send the same thing to your Bluetooth device on your phone, for example. Your display, you don't have a display on your altimeter. And then the main thing, the final thing, is the OLED display itself. I don't think this 2.75 works. I think it's integers here. So it does accept this though. So you can play around with these numbers to change the text size, position. And I also have, if the altitude is less than 10,000, I actually print the direct altitude in feet. Otherwise I divide by 1,000 and show it to 2 decimal places if it's more than 10,000 feet. So that's there. And the last part is really to print all the stuff that I can see on the OLED display. Is printing out the altitude, which is here, and then I print out the altimeter setting on the right top. Then below that I print out the temperature, and finally below that is the dew point. And then I display all of these, delay by 100, and then I go back. Essentially it updates every 10th of a second, and go back to the beginning of the loop, and it keeps doing that. So something to watch out for is only I've seen some occasions where due to noise the altimeter setting automatically increments or decrements without any rhyme or reason. So you have to make sure your board setup is good. Sometimes if I connect this USB to my PC, it doesn't program, or it might reboot automatically. All kinds of weird stuff happens. So I'm still not sure about how good this Arduino hardware is for all these clones that they're making. But if you get it to work, I think it does work, and it seems to be pretty accurate. So I hope this gives you some idea about this program itself. there's scope for improvement, scope for modifications. So I think I would like to conclude at this point on the software portion. Hopefully you have better luck sometimes than I do on this programming this thing, having a stable output. But so far it seems okay when I connect it to the external power supply without the PC. For the most part, it seems to run. I've seen one failure of one board where it stopped working suddenly for no reason. I had to replace that Arduino on that, and hopefully this new one continues to work fine. So we are come to the conclusion of this project. Just a few remarks before I end it. This project showed the implementation of a sensitive and accurate altimeter with a hardware adjustable altimeter setting using a rotary encoder. I didn't want to actually do it in software because you can't program the altimeter settings dynamically unless you have some two-way type of communication with the device. So I didn't have that for this particular implementation. The components required are inexpensive and the programming is fairly straightforward to get basic functionality. Further software improvements could be made to improve memory utilization, add features such as filtering, range settings, and so on and so forth. The prototype needs a more robust enclosure. Actually, there was no enclosure here, and hardware could use a dedicated PCB along with more hardware switches to add more settings. And finally, I'd like to post the Arduino code at some point when I get a location to do that, and I will do that as soon as I can. Please check the description for download information.